Whatever. You can use the remote.
Oh, they have a remote?
Yeah.
Oh, okay, that's good, like, go there and see how is their remote.
They said yes.
Let's do it this way, remoting is easy.
They are receiving the funding, but those components are the same.
So let's change the topic, from energy transition to a new buzzword, digital twin. So you guys probably know what a digital twin is, but this talk is about the challenges that we have at the moment on the modeling aspects of our reservoirs. It can be anything. It can be a hydrogen field, it can be a CO2 field, it can be, but the way I did it, because most of the examples are in petroleum fields, oil and gas field, so I'll put it that way. So the question is, what are the challenges? What are the questions that can be answered? And where the AI has to be there. Like AI, everyone talks about AI. What goes to the physics? What goes to the simulation? What's if AI going to be doing everything, or the simulation going to be? And I talk about the challenges that we have in the simulation and also the solutions. So what is digital twin? A lot of people have a different understanding of it, but digital twin, really the way that people like to have it is to have your mechanical field, or like whatever, or windmill that you guys were talking about it. You have some sort of a simulation in a machine, like in your laptop, and you deal with it, you play with it. That's the point of having CFD. Modeling like a plane in the CFD, like instead of building those big wings and put it in the wind test. So that's possible, but that's quite expensive. The same thing for oil and gas stuff. Like you can have these wells, and we try and error different tools that we have, like millions and millions of dollars goes, or we can model it properly and use those models, like as software models or code models. So, and that part AI cannot help, because AI needs the data, historical data, then you can train with it, and then hopefully you get something out of it. So this is a structure that we are really doing these days, is data preparation for these oil fields. So most oil companies now have good dashboards. They have the data centers that we talk about, the efficiency of it. So they keep the data now. It wasn't like this 10 years ago. There was no digital data. Like even started my career, I was asking for LAS files for these logs and stuff. Some people give you in PDF. There was not even give you a notepad in that time. But now everything is very nicely stored. It's still hard, especially in the smaller company. Once you want to get the data for something, it's still like data organization is not that nice. But all these big players, they are passing that one. Like they have a good dashboard. They have a real-time drilling data. They have everything. So the next phase that all the world is in this one, like modeling and prediction. Why I say modeling or prediction? Because predictions is sometimes they do different teams. Modeling is more history matching, and you want to do uncertainty analysis. Some people like talk about prediction use AI. But really is that part of that we are stuck at the moment, and that people like start working on it. There are so many issues in the way we model the oil and gas aspects, more issues on the AI. So that's the part we're stuck. And hopefully once we resolve that, we go to uncertainty evaluation, and then hopefully we can get to automation. And once we have automation, we have this digital field. Like there is no oil and gas. There's a chat GPT that running your oil and gas field. That's the future. And that's the aim of all the things that we do these days. So what is the problem in the important problem? What's we are trying to calculate in model? Really, we're trying to calculate to predict the future. So if you know what's going to happen tomorrow or what's going to happen in a year by changing this bottom oil pressure or changing the temperature or changing the injection rate, all the problems solved. Okay, so we trying to get to that point to have some tools has amazing predictability. So that's what we're looking. So you don't, if there's this, we get that's wrong, but this, it can be right. So what we do at the moment in oil and gas industry, using whatever tool we have, and we try to history match it. The problem in that is, it's not a problem. You have to history match, but we're not doing. If we even not capture the physics right, we can't history match it. Okay, so that's like we're changing your rel perm, for example, and the rel perm is not even close to what we have in the test, and we're changing it to get the water rate match, and we're changing permeabilities. We do whatever we do to get the history match, and the history match is to get this period of life matched to the oil rate or whatever we have. And based on this, we have this model that we tune it. It's pretty much like an AI trained, and we go and predict the future. So this is the example of exactly the same thing that we've done. This is Calgarian example. This is on ICD because most of our projects are on ICD. ICDs are these inflow control devices. This guy did the ICD, and they did the design. This is before ICD, and this is after ICD. And they see the huge improvement. They're like 50% improvement. For the people who are not familiar with SAGD operation, they call that flush production. So after you stop these wells and you put the ICDs, because you didn't produce for sometimes in these SAGD operators, then you heat up that rounding and you have some production. And then once you start the well, you have this high oil rate. And a lot of these vendors come and say, oh, look, how much you increase the oil rate. But they call it flush production. So that's not real. That happens in a few weeks and that's gone. But the adjacent well to the one I'm just showing you, they did the same thing, like history match and those stuff. And they designed these ICDs and they put it, and what they get they get negative. The same geology, the same thing. So it tells us the approach that we're using now, no matter if we have a good history match, it's just something wrong with it. We're not following the physics right in a lot of these stuff, and AI cannot help us in those aspects. And normally, the questions comes in the longer period, because the longer period we are talking about EUR, recovery, ultimate recovery stuff, rather than what's tomorrow is my rate is. So if your focus is this, and if you do exactly the same pattern of history match or whatever we do, you are probably right, because the model you provide would not go wrong in few months after, but the things happens in the future. So this pattern gives you with that, like your new design, you go follow this, but really you have to do this and you be this. So this is a problem, like just matching or history matching without really following the physics. It can be on AI, it can be on our software simulations. So we have to follow the physics, and there are key bottlenecks in the current modeling of everything we do. And these are the key ones. I'm talking it from the well aspects, but there are so many others on the aspects, but these are the three main aspects that I see, when we try to solve it. Is one is multi-phase flow. What we modeling in the vertical sections normally, with all these academics works, with all these industrial works, we're not even close. Like the depth of PV measure, like liquid holdup. Who was working on liquid holdup? There was one student yesterday.
Yeah.
Was you?
No, it wasn't me.
There was someone else that was working on liquid holdup. Why we working on liquid holdup if all these multi-phase flow models are right? But the problem is there is all these academic works been done, not being coded in these softwares. That's one of the biggest problem. And we never validated with the historical field. We did any flow loops, and we never go back and see what the composition effect is. We test the flow loops with the air and water. The guys showed me yesterday, like that's even Tulsa is the same, huh? But you go in the field and you have condensates and the gas, different viscosity, and that changed the whole story. So that's one of the vertical section multi-phase flow. The other ones, there's a key, there was a student here also talking, using the console, and he got the same issues. And it's a grid connection, and that's how you connect the wellbore to the reservoir. And I focus on that in this presentation. Why is that wrong? The way we're doing it currently is super wrong, and how we has to do it. So grid connection from the well to the reservoir. There is no software that these things be coupled, implemented. There is an equation, set of equations that connect the wellbore to reservoir that we have to couple. And the other one that we never think about it, but now with new completions that we are heading to, is segregated flow. So we have these three valves inside the well. It can be a perforation inside our shale oil fracturing also. It can be anything, but this is just for like an oil well now here. If you produce oil and water and you have a segregated flow, or if you produce a gas and water or gas and liquid, this one only see gas and these two only see liquid. But what we model, in all the way we do modeling, we mix them up. We treat this as a mixture. The pipe is a mixture, and we get exactly half of it, 1/3 to this as a mixture. But that one only see gas. The other two just see the liquid. And that's huge thing. And they see the effects in the North Sea and the Middle East. Like the way the model is totally different. So that they see it, like there's a real field data that you can't see, but I can't share it with you guys. But then you see that the effect is huge. The effect is huge. So let's talk about it on the multi-phase flow. And I go to the history and I give you some of the solutions that we have and some of the other stuff. So in 1950 pipe, there are empirical equations. What is empirical equation? Bakes-Breedless one, like those type of equations. And 1950, all these empirical models came into, like all of them is like around 1950, 60. We didn't have like computers, right computers in that time. And what we using today, Agden Brown, and still like all these software like Agden Brown, Bakes-Breedless, and those. So that's the problem. The other one is 1980, the better models of mechanistics, like Ansari, Hassan Kabir, and those came into play. There's no software using this. Okay, so that's a challenge. So we're not using even the stuff that been validated and we can use it. Maybe in an academia, but not in the commercial softwares that industrial people use. And then we come to transient in 1990, and the only software has it is Olga. Okay, so Olga has a transient, but they had it for like one aspect, water and steam, and they do it for everything. They never validate it, and they get the mechanistics on this. Olga is a software that Schlumberger bought, and they're using it. But we had a transient for the reason, like once you have a pipe open and closed, that's for nature. And there are new things that came into play, which I like it a bit, and I see the potential of implementing it. We implemented in some part of our software is analytical multi-phase flow. So these are some sort of AI, but in multi-phase flow. So there are like you can see the biggest scale data, and you can use it. And a friend of mine, Dr. Nagu, is one of the pioneers. And we have some of those models. There is a reason for every of these. Forget about this. This is only give you faster, but you have to at the end to get to any of these. So look at these models. University of Tulsa had a paper that put all these models, like empirical models, and they give them a point, like it give them a value. So if you're smaller, that means that's a good one. If you give up one, then you cannot trust it. So this is Duns and Rose, this is Beggs and Brick, this is Orkowski, and this is Mokreja and Brill. These are four main empirical models that all these software have been using. And you see the numbers, 6, 4. If you are, this is times it to 100, and that's a percentage of error. You just get like 600% error. So on these stuff. And this is like on, if I go one back, these are the number of experiments that they collect like 1,300. These are massive amount of data. And Tulsa is the only one who could gather that amount of data. So they test all these. This is on annular flow. For example, these are on everyone's, you can read on bottom. Like if you have, I can share the PowerPoints with you guys. These are the type of the flow regimes there are. And these are the models. And these are the number of test experiments. Okay. But the funny thing is, like the Hagden-Brown is the only one that really works okay in like dispersed type of stuff, not in the annular and the slug, but in the ones. And this is Hassan Kabir mechanistic models, and you see it's amazingly like if it gets to 0, that means no error. On kind of an annular, this is a slug. And on annular flow, which you have mostly gas and then slug, the error is still like tremendous. So that's what we are. This is a good article to talk about all this stuff. And story model that they developed, they call it Tulsa model. They develop it for the annular flow, and you see the 0, and you see wherever they have an annular, they got lots of gas. This is a real good model to be used. So what do we do? What's our solution is, because these mechanistics are slow, okay? If you want to do like 10 years of history matching of one data, probably not really smart to start with these mechanistics. So what we suggest is to just go on empirical models, because some of them are good for some aspects. So you see Hagden-Brown works in dispersed bubble and those stuff. So the Hagden-Brown is good. It's not that bad for like using it for conventional black oil. Once you got the gas, no. So you use this one and then move to mechanistic for the final touch or final understanding. And you have to still do some history match. So that's what we do. And we also did a lot of changing on these mechanistic models to make it more stable, because a lot of these mechanistic models they have these boundaries, and the software doesn't like discontinuities, and you get convergence issue. So you have to recode whatever they give you in a paper would not work in the software like us. You have to recode it. and you have to make it somehow smooth on the transitions. But the other thing you have to know is going always so complex would not help us. What that means? This is the actual field data, and this is a Reynolds number, and this is a pressure gradient, and those are actual numbers. And you see Olga and Lida and Ansari. All of them didn't go good, and on this thing, and I think in this aspect, the heat transfer was the issue, but the paper didn't provide any data that can evaluate it, but it shows the Olga and Ansari and this Lida is also like a transient model, would not get the right answer for you in the steady state cases because they designed for transient. So not always go towards the transient, not always go, because you get a lot of other uncertainties. Like if you have ever run Olga Lida, you have another 30 parameters that you have to provide and you don't know what those are. And those are mostly for like something that only academic people knows. Okay. So you may run it wrong, or you get like not going always towards the complex if you add it back.
Sorry to interrupt your meeting. There's another meeting in her afternoon,
Oh,
and they ordered lunch. She's wondering if she could come in and set up.
okay.
Oh, yeah, all right.
Is that okay? She
What
wanted
time is it
to
now?
take just a couple minutes. Yeah, you can just put it right down there.
Okay, so I like that. So I just want to see that. But these are the parts like really going towards mechanistics models. But this is the gas lift project. And this is a gas lift project, and these are real data. And this is gas injection rate, and these are actual data. Okay. But the thing is, like in this chart, we analyze it and show, okay, so we go to the mist flow. We don't want to put that much gas lift go to mist flow, and this is the range. But the things that you can capture is this point. So going from annular to a slug create a shock in your gas lift. So you at least understand you don't want to go this low. You don't want to have your gas lift smaller than this. You want to be above this. And these are actual field data, and these are simulated. These lines are simulated. So then they help you, okay, I don't want to go that. So that part Bayes wave, for example, cannot, even if you tweak with every parameter, you cannot see these changes. So grid well connectivity, that's the part I love to talk about. What we do these days, 99% of us use P-span, and I'm going to talk about it. And then, and what P-span does, I didn't put a picture, but what is P-span? Like P-span developed this formula in 1978. It's just like a well test formula. It's just a well test IPR. And we assume this grid is our reservoir in that formula. And all these sockets, you put the grid, the well location around the grid, and they have this formula. So that formula developed for a single phase. And assume that whole reservoir or whole that grid got the same saturation, but the same pressure. All of these are wrong. It works 1978 because all of our reservoirs didn't experience a lot of gas liberation at that time. We didn't have shale oil. We didn't have complex water flood injections. And all of our permeability was amazing in that time. Now we're dealing with a lot of low perm reservoirs. And so depletion, the pressure drops is huge. So what we expect these days is, because the permeability is smaller in all of the reservoirs that we're producing right now, a lot of these reservoirs, we suck the pressure below the bubble point. And the gas liberation happens at the samples. as a result of this gas liberation and the sand phase, you have a local rel perm reduction around your wellbore, around your near wellbore, that you have to consider. Okay, so you have to model this. You have to be able on this, and this is 10% of the Middle East will also experience that. Like,
Excuse me, what causes the reduction in permeability at the sand phase?
no, I'm saying that because the permeability of these reservoirs are lower,
Yeah.
like that we have to suck harder. We have better pumps now, and we have lower perm reservoirs, we suck more. Yeah, we don't have like 10 Darcy reservoirs anymore.
Yeah.
In 1978, everything was like that.
Yeah,
Okay.
what I'm asking the question is because I'm very sensitive to issues of formation damage, because that is my research.
Okay. This is not the absolute permeability.
Yeah.
This is the rel perm effect. So you suck it more and gas start, like you go below bubble point, you start having the gas liberation around the wellbore. And you start seeing in the pores. And that gas comes and your rel perm is dropping. And it happens in like 5 centimeters away from your well, 10 centimeters away from, but that's caused a lot of, it's like a skin effect for you. Yeah. But it's a positive skin. But it comes, you have to model, you have to be able to model these. In shale oil, always happens. In the shale oil, you have a different way. You go below dew point, and what happens? You have a condensate buildup. Okay, that's what always people talking about condensate buildup, and you can model it. And if you go to these conferences, a lot of people talk about condensate buildup, but they don't have a solution for it. The solution is have to model the near wellbore or near fracture. You can't use pieceman, single phase, without assuming anything changing. All the grid doesn't have the same water saturation. What is your grid size in normal days? Like it's like 5 to 5, and you assume all the water saturation is the same. All the your gas saturation is the same, but no, it's changing around the wellbore, especially. You have to capture that, and the pressure is changing now. The pressure is not like 1978 that you assume this is my reservoir, and you put it there. And the problem is like if you go to Stanford, for example, 99% of the people work on reservoir simulation, how to make matrix faster, how to segregate the model faster. If you go to Tulsa, that's the best university on this multi-phase, well, everyone's worked on like these bubbles coming and this, but the industry forget about what's going on. Like they forget about like this well communication with the reservoir is the biggest concern, and we're not doing any work on it. Okay, and there are solutions for it, and we capture those. So you do this finite volume or finite difference for your reservoir, and I say you have 2 jars. You have 2 jars. This is your reservoir simulator, and you have another jar. We call it pressure tracer method because that's a method we use for modeling and the grids connected to the wellbore. So you have a jar that connected to this. That's the grid connected to this, and the jar outside reservoir. The final difference of the gridding and stuff. You provide it to this near jar, this reservoir grid, and you produce from this one. There is no issue with communication on this, all the problems in here. And the other problem that also is there, if your well is located here, all of these models only consider this grid to give you the rate. But this well is like connected to this boundary. You get the same amount from this one and this one. So in this method, the pressure tracing method, it's not just one grid giving you a rate from the reservoir. The adjacent grids also give you, and also the direction. Because all these models, like a pieceman created for vertical wells, is the horizontal well, the direction of the well and location of the well is also important. So it captures all those. And also capture the rel permission. Okay, so that's the one. And that's really important in shale oil. and thermal projects, because in thermal recovery and the flashing of a steam and in shale oil condensate well cups happens in like few inches away from your wellbore, and that causes a lot of differences. So this is what really the Peaceman does. It's like assuming the constant IPR, the straight IPR. And if you guys remember the Vogel's IPR, Vogel's, no one's here? Yeah, why people Vogel's really created in that time? It's an empirical equation, but really they developed it in that time because they see if they go below the bubble point, they want to have some IPR. This is production engineering IPR. They say they can't go with a straight line, they have to do something. So that's what we do inside the grid connection. And one of the interesting part of this model is if you consider geomechanical effects, and you can, if you consider the geomechanical effects and also go very low on the bottom hole pressure, your IPR goes negative, like it goes less. It doesn't go like this, it goes something like this. So you reduce the IPR by sucking more and more. It's not giving the higher rate. And also, you can also capture your geomechanical effects. So geomechanical effects play a really big role at the lower bottom hole pressures. So the good thing about this approach is you can have multiple wells and you have your wellbore grading separate from your reservoir grading. So what you need in water flood, for example, you have these small, you want to really capture in these ICDs, for example, you want to have your grids around the wellbore as 1 meter. Okay, if you want to see how the water saturation changing. And you can have the wellbore as 1 meter or 20 centimeter in this case. And you do 8 years of, you do 5 years of operation in 2 minutes. That's what happens. This is it's better than my laptop that I have it. But you take 2 minutes, you get the ICD design, and you can capture like 20 centimeter. So you don't, if you want to, it's a millions and millions of grids if you want to do it with the old ways. And this is one of those wells in model. And the other thing is also, this is a real well actually, and it's in the Middle East. And so you put a packer here, for example, and this was a fracture here, and this ICD choke it here. The other thing is that you have to capture in these new problems is annular cross flow. And so if you do it in Eclipse, this is what your P would looks like. But your P is something like this. This is packer, this is packer to packer, and you have 3 ICDs. And this is the upstream of these ICDs. What happens in Eclipse? Like, for example, like all of these simulation softwares, whatever you produce in this grid comes to this node. But this is not what happened. Whatever you produce here come to this compartment from this packer to packer, and these 3 has a competition to get it. There is an annular flow, annular in here. There is a gap there. That's what they call it, annular cross flow. That's a competition that you have to model this competition between these wells, between these ICDs. It's not just everything comes here, it goes here, everything comes here. That's not. So I'm not talking about it, but that's the thing, that's a big thing if you want to go to this thing and you model it. If for North Dakotan people, where is the point of this? A lot of people talk about, these guys have a nice lunch actually. The thing is like multi-stage fracturing for EGS.
For vacuum as well.
For Bakken and for shale oils, that's what I want to mean, like for EGSN. Everyone say, okay, we do multi-stage, but what do? You put rates exactly the same, like once you pump the liquid, that's not the way it works. The fracture is the stiffness itself. So you have if you have a bigger fracture, you have less stiffness. So that's one, want to take more liquid. If you have a smaller fracture, you want to take less, it's resistant. And that's exactly what happens here. And you have a perforations with different sizes. So perforations are like ICDs, but your formation also have a resistance. And that resistance, because of, if you have a bigger fracture, you have a bigger surface area and your leakage is bigger. So you have less resistance. So exactly the same problem there. That should be captured exactly the same solution for it. That's what I'm saying. It's not just ICD, that's exactly here. And you see a lot of people talk about the preparation this and we model it, the fracture doesn't look. A lot of it because the distribution of the fluid that you're modeling is not what it goes. So that's what I put here. If you have a no flow boundary, you have to model the no flow boundary and also the cross flow. So this is the more restrictive and this is less restrictive. So no flow boundary always comes towards the more restrictive because this one doesn't want to get flow. This one want to get all the flow. Okay. You get back to this again, like what we focus and what we should focus. And the AI also need the story and the history, but it's never can compete with physics because physics always is predictive. AI is predictive once we got massive amount of data. And the problem with the AI, the way we're doing it currently is the data, near-term data, has the biggest impact on our future predictions. But that shouldn't be the way it goes. So this is also the well, this is the well you guys modeled yesterday. I have to send you the solution because none of us model properly. But this is what happens. That's a real field. And you see in these new fields, we have shale, we have low perm, high perm, low perm, high perm, low perm, high perm. So the one way is just averaging everything. One way is to make the grids 1 meter, 2 meter grid size, capture this variability, and that could be the way. And then once we do these stuff, we have to do uncertainty analysis always. So this is uncertainty analysis on this. This is a Monte Carlo. So normally we don't have a lot of inputs, so we have to do uncertainty analysis. This is what we, the red one is the history match and predicted based on the values we put, but that's uncertainty on what's going on. This is huge. So then that goes in our financial Excels that we provide to bank. Segregated, talk about segregated. You see gas here and the flow here doesn't see the gas. And this is what happens. We always model liquid hold up in these models. Like all the empirical models we also model. And but the thing is, we mix everything to pass it through inflow control device. And that's not right because these two are only seeing liquid. This one see gas. If you have oil and water, one of them see water and one of them see oil. So this is the method we did. The system is the constant delta P. These are parallel FCDs. But the difference is those two see the different density and different rate. So delta P is constant, but your amount of rate that you're getting from those to honor that delta P is different. So only the bottom parts see the liquid. So the only compete against the rate on the liquid. The top one, see the gas. And that's the difference. So if you remember, like if your VLPs stuff, this is, in our software, you can do also the nodal analysis. So this is IPR. This is without the tubing. And the green is the segregated, and this is the mixed one. This is what you assume everything is mixed up. Less time it takes to get this. But you see the right answer is this. So different. The delta P you're getting and the rate you're getting is totally different in the segregate. And the other thing is, we see these nozzles. In this conventional reservoirs, the size of my finger is the size of the well in this room. Huh? You don't have many, like this, you have to see that scale. And these nozzles are very tiny and they are located. But the thing is, you have to see the reservoir from the point of view of the nozzle, not from the point of view of the reservoir. So you have to go even deeper and look to see what the interactions have happened. So the nozzle is your view to your reservoir. So the CFD is the only way that we can capture these modelings. But there is limitations. So as yesterday I said, you have a laminar regime assumption and turbulent regime assumption. These dots are actual data. You see in the smaller Reynolds, like 500, this blue one captured nicely. And in 6,600 at 1500, the turbulent model captured nicely, but not the laminar. So that's why we use different formulation in CFD. But how we connect these stuff? There is a discontinuity. There is a discontinuity between these data points. And as I said yesterday, the only way to, is to have some sort of a curve fitting on it. I bet most of you were here yesterday, and that's what we do. And then you get the results. And for the geothermal people, like also heat transfer is the biggest component, and that's also another. It takes another session to talk about it, but especially the wells that we have in North Dakota, and I know you want to work on EGS, but a lot of these operators want to do coaxial. They just want to say, we have this deep well, and we want to put this tubing, and we inject hot water, cold water, and get it hot. And so this is the pressure profile. You have to inject it, and you get it from down here. But the temperature you injecting, and you're getting it from this here. So I want to talk about slightly about this. So this is what's happening. You inject from here, and you get a warm, and you get it back, and the same thing on the pressure. So the thing is, this type of heat transfer modeling is really complex because there is a tubing that these two other sides are talking. So you have to make a loop and iterate all those. And you also know the temperature at this point is the same. So the way we do it, you know this point, you don't know the answer at this point, you don't know the answer at this point, but you know the heat. There's a tubing heat loss and heat gain, and these are the same. So you do like 200 iteration for this tubing and this tubing till these two temperatures get to the same answer. So that's the way we solve it. And that's the only way you can really solve it, because you don't know this temperature and you can't force it. So you have to, that's the way you have to solve it. So, and for pressure it's easy. And the problem is you have this enthalpy change and you have this enthalpy of the water, and this is your enthalpy change across it. But what if you want to inject CO2? What if you want to inject another refrigerant? So you have the flashing that comes in your model that disrupt your pressure calculation. And those are also has to be modeled And the way we do these days in the modeling, you never can converge. You have to find. That's what we're working on, and we're developing always like to honor the enthalpy and the flashing and also always be convergent. So at least I know 2 clients using the other softwares. They never. It takes 9 hours to initialize, and then they run it. It comes out, and they do CO2. So that's the issue. Like that's a lot of things happening there because heat transfer is a challenge. Heat transfer plus pressure is also a challenge. So the conclusion: solution is available for at least 90% of the things. We are not looking for it. We see using Duns and Rose, which has like 800% error in a lot of these commercial softwares.
800% error.
That's what I'm showing now. Sorry, like in like gas cases, like annular cases.
And for the
Not in the-
correlation for steam and water, we using the same. I didn't see new correlations for steam and water, how affect the temperature, but more than the temperature is the only we have just 2 phases, no? And
Yeah. Actually, that's the other thing I want to say, like especially in CO2, like all of us talks about Peng Robinson and SRK. Yeah, and all the software have it. But nowadays, a lot of this funding, and one of it is DOE, and NIST has a very nice model for CO2. We call it GERG, G-E-R-G, and 2008. And they develop it, like every year they come up with, and so that's handle the CO2 impurity and we have it in our software, but where no one's had. I see like people like using SRK and Brainwave, the error is about 30%. On water, IAPWS, you heard about it? They publish the formulation every year. But we are still using 97 version, like every one of us, because that was the last free version. So that's something we have to go also do the change. And the problem is a lot of these things develop in these government funding things. They come on the paper. Once they're not coded, there's no point. Like you can't really get it into something. Like they just come. Yeah. But at least we have a solution. We have these models. It takes a time for someone to go and put it in these new softwares. What was the second one? It was honestly. And a lot of problems we have, for example, like this geothermal thing, we cannot find the right answer or find the final answer without fully integrate every element. So ICD is one of those. You should have a CFD modeling, you should have a wellbore modeling, you should have a near wellbore modeling, you should have a reservoir modeling, and you should even model your vertical section because you have a pumps. Everything's interacting. It's not like you say, I just want to model this part separate from the others. It's a fully integrated problem. And a lot of problems these days we have is fully integrated.
Yeah.
And if you want to get to the real difficult field, that's the only solution.
And question, yeah, because for example, in the oil and gas, in water treatment projects, we use regulated valves to optimize the sweep. No?
Yeah.
And now in I'm talking about geothermal, with that we want to do the same because we have to avoid short circuiting.
Yeah, in EGS, yeah.
Or in geothermal, conventional geothermal is the same.
Yeah,
For
yeah,
the
the
reason
same,
they inject tracers, they need to start. And I don't know if for EGS it's convenient economically, no? But for geothermal, conventional geothermal, it's convenient because they know they are not working with natural fracture reservoirs, and if they have
Exactly like what?
yeah, it's similar. It's close.
Yeah. It's not, yeah. But this thing I said, it's not just for the ICDs, I'm saying it for like other aspects. The reason I'm always talk about ICDs in this stuff because I got so many examples on that field. But if you want to design a pump, it's in the future. With the tighter the margins are, you have to use more and more integrated applications. Okay, so by that, I'm done.
Thank you.
Thanks for coming.
Yeah,
At least
I was.
Make it. It was raining and.
Yeah, I was online. I joined.
Oh,
yeah. But I joined online.
So I wanted to find out, well, one very interesting thing I have noticed while I'm doing my research information on this, there is no dedicated softwares for formation damage modeling besides I think besides your chemical models that treat inorganic precipitates and that.
Oh, there is not.
There is none. I've really searched and talked with you guys about.
Okay, let us know what you want and we add it. We don't have it too. Like we didn't know there's any concern about it. Like we're open to add like anything. Like if you have something that you think that we have to add, we can add.
Yeah, because
We're quite open.
Recently, I did some research in Minnesota on the particle size characterization. Let me grab something to show you.
Yeah.
Oh, you're going
No,
to the
I
lab.
don't want to just.
Let me see if I can get my flashlight back. I give it to this.
Yeah.
Okay,
You lose it back.
Yeah.
You lose a lot of my.
This is a sample of produced water.
Oh yeah.
Yeah, it's a sample of produced water, and it has a lot of particles. They cannot be seen in the naked eye because they are micron size.
Oh okay, yeah.
Very small. There are lots and lots of heat. So my research is actually the interaction between rock
And this one.
and this one. Because this is what is actually used for hydraulic fracturing. Nobody wants to purify the water because it's expensive.
Oh yeah. That's a waste of time.
It's a waste of
Money.
Yeah, and the thing is a waste of money, but they could be using even more. Or let me say that they could have produced more if they had the time to look at the particles in this water and the effect that it has on the permeability of this water. Because we're injecting during hydraulic fracturing is what this water under very high pressure. And it doesn't only have colloidal particles inside, it also has other things like friction reducers and
Those like
additives.
yeah.
So we did a particle size distribution. We try and compare this sample is in the video graphic. It's a dolomite and silt stone, so it's a comment. This is very tight. Very tight. So
Why is it
the permeability is in micro gases.
Uh-huh.
So we have to
That's
factor this.
0.0001.
Yeah.
Anything to flow here, we'll have to really factor this. Then what happens is that.
Thanks for coming.
Yeah, I didn't understand half of it, but the AI side though I connected with, so I thought that was really interesting about how it's being implemented or utilized.
Yeah. It wasn't about the windmills and those stuff.
No, it's okay. I'm more electrical than petroleum, so it was kind of interesting to get familiar with some of the terminology.
Yeah, they want to keep us up.
Oh, is that?
What is this?
I'm not only with my experiments all over the place. Everywhere I go, I carry my samples and my things.
Yeah, what was that?
Yes.
He was showing me like
a lot of questions.
Yeah, and I'm proud of this guy.
Okay.
He's trying,
Okay. Thank you very much.
but he was not trying before.
It's him who spoke to me one
Yeah.
time.
Yeah,
And from there, everything changed.
I'm happy with you.
Yeah.
You were three. You are the only one.
Yeah.
So keep it up.
Thank you
We've
very
seen
much.
all of you.
Okay.
We've seen what you.
Yeah, because although we are many, it looks like you guys are always.
No, see, I know what all of you are
I
doing.
agree.
So
Yeah.
before I wait,
Yeah,
I'll be back. So
sure.
He said we could take one of these for lunch.
this is no.
Yeah.
It's coming first. Yeah.
I saw you in LinkedIn. I know. I was guessing is that you are not here. So, yeah, it looks like that's you.
Please take him to.
Sure, sure.
Let him see. I'll take him to- Okay.
Okay, but you have to do it interactive, like, because we never, model the,
Can we talk about it in the office?
yeah, let's go, you got a key, let me go to.
Yeah, I know, okay. Sorry, I'm a, okay, no.
I was just gonna say, I wonder if it'll be in here. So there's two chef salads that have no meat or cheese and one of them is for Rebecca. And if somebody else wants the other one. I just ordered all this. They can have all ones for everyone else.
Oh, okay.
And then-
Oh, for you, you get
It's still over there. Yeah. I guess they're just trying to find their own. Gotcha.
it.
I didn't see him. I don't know if Rebecca was meeting him or.
Pretty decent.
Hopefully there's a constant. Well, you get this. Probably just.